Okay, so where were we last? So we finished hydrogen, and again, I'm just going to, again, we're going to see these molecular orbital diagrams a lot. The idea is that we take, I'm just going to label my hydrogen as HB and HA at some distance R, and I'll just put my B atom and my A atom here. When they're separate, what energies are those atoms at? Well, we assume that the wave function for this molecule is a linear combination of 1s orbitals for each of the atoms, one at A and one at B. So what we start at, again, is our 1s orbitals. So the energies of the atomic orbitals that we start with, they each have one electron because they're hydrogens, is at the energy of the 1s orbital. And then when we bring them together to form our molecular orbitals for H2, we get two new orbitals, two new wave functions, one that's higher in energy and one that's lower in energy, like so. And by Hund's rule, of course, the electrons in AB, or H2 in this case, all fall into the lower one. And we call this a bonding orbital because when you add the two wave functions together, they interfere constructively. So there's an increase of probability of the electrons being between the atoms, which we call a bond. And then you form the opposite, called the antibonding orbital, that's higher in energy. And of course, that's antibonding in the sense that it's literally the polar opposite of bonding. In the antibonding orbital, the electrons want to be as far apart from each other as possible. I have a bit of notation for these. So again, what the bonding orbital looks like is a 1s orbital plus a 1s orbital, which is basically adding two spheres together. And you get this kind of oblong orbital, wave function looking orbital, where the atoms are at the focuses of that ellipse. And it's cylindrically symmetric. Like that. So this is a bonding orbital, right? The idea is that now the electrons want to be shared between the two atoms. And this one, the antibonding orbital, is the idea of 1s minus 1s, which is kind of like adding a positive function to a negative function, so they deplete each other when they overlap, and you end up getting orbitals that look like this, where the electrons want to be on the outside, push away, an antibonding. All right, there's some notation that we use to label these orbitals because, as we'll see, orbitals tend to form very specific. When you add atomic orbitals together, S's and P's and D's, they tend to form molecular orbitals of very specific symmetries. So when you add two S orbitals, again, remember S kind of, this is not what it stands for, but I often think of S as in being spherical. When you add two spheres together at a distance, you form an ellipse. And so typically, the resulting orbital that's formed from the addition also exhibits some sort of symmetry that looks like spherical symmetry. And again, it's just an ellipse where ellipsoid, it looks like a football, a symmetric football, where the A and the B are the focuses of that ellipse. And this is cylindrically symmetric. Or sphere, it's actually really it's cylindrically symmetric. And we call these sigma orbitals. And so the term we use to notify the combination of these cylindrically symmetric molecular orbitals, these S-like orbitals, we call them sigma, or we use the letter sigma. Sigma orbitals. So typically we call S orbitals, when you add them together to form a molecular orbital, you label them as sigma, like that, sigma. Okay, and likewise, antibonding orbitals of the same symmetry, this is also cylindrically symmetric as well. If you rotate around the axis of the bond, you get the same thing. Right? That's what I mean by cylindrically symmetric, that if you rotate the orbital along the long axis of the system, you get the same thing back. It's symmetric around that. We tend to write these with a star on top of it. So an antibonding orbital tends to be whatever type of orbital it is, star. So I'll say bonding S-like orbitals are often called sigma orbitals, and antibonding ones are sigma star orbitals. All right, this is common chemistry notation. Okay, so if you ever look at studies of molecular orbitals in organic chemistry or biochemistry or whatever, you'll see things called sigma. Orbitals are called sigma star. That represents that the orbital has this cylindrically symmetric thing. It looks like a sphere, an elongated sphere, and it has the symmetry of a circle. All right, so we call those sigma orbitals, and today we'll see another type of orbital as well, coming from the p orbitals when we add p's together. All right, so we'll look at that in just a minute. There's one other small piece of notation that I'm going to add. This is something that is very common in small molecules, but there's an interesting point. I'm going to skip that. Actually, let's not worry about it so much. Let's just stick with the sigma. Okay. So now, this is all I have to say about hydrogen. Right? This is just qualitative, right? I don't really know how much this splits by. I have to do a calculation to know how these are or measure it in some way. Measure how much this occurs, how much bonding, how much the bonding strengthens the orbital, how much it lowers its energy, right? So quantitatively, we have to do quantum mechanics to figure out the actual scale of these energy changes. But qualitatively, this is exactly how it works. Now what I want to talk about, let's try a more interesting molecule. All right, so we've done hydrogen. So let's go down a row. All right, so let's go to the 2s, right, the second row of the periodic table. And I want to look at 2 molecules today, nitrogen and oxygen. Right? Of course, the most common diatomic molecules on Earth are N2 and O2. And I want to do molecular orbital theory on these. Okay, so let's think a little bit about let's start with nitrogen first, and then we'll move to oxygen. Okay, so let's start thinking about, what atomic orbitals do we have in nitrogen? Well, let's think about nitrogen's electronic structure or configuration. 1s2, 2s2, 2p3. Is that right? Yeah, 2p3. Okay. So now when we combine 2 nitrogens together, well, what do we have to add together? Well, remember we have to construct atomic orbitals for each of our atoms and then add them together to construct molecular orbitals. But now we have electrons in 3 different orbitals. So let's think about that. So that means that our wave function for nitrogen, or let's say our wave function for a nitrogen atom, that we're going to combine, our atomic orbitals that we're going to combine to make molecular orbitals, we're going to want to have a hydrogen function for the 1s orbitals, hydrogen function for the 2s orbitals, hydrogen function for the 2px, hydrogen function for the 2py, and a hydrogen function for the 2pz. Right? Now we have 5 orbitals that we want to add together. Okay. Now again, we can add more if we want, but these are the ones that have electrons in them. Okay. So now how do these add together? Now we're going to add 2 nitrogens together, right? And so now the question is how do, of course in hydrogen what happened, we added 2 1s's together to form 2 sigma orbitals. Right? So what happens when we start to add all of these other orbitals together? How do they combine? In the same way. And there's some nice rules that we can make that I'll write over on the side of the board. Right, so the question is how do we want to combine these orbitals together to form a good molecular orbital picture? And here are some simple rules. One is that valence electrons, right? So that's, in this case, the valence electrons are the two S's and the two P's. Valence electrons determine bonding. Of course, that's what we learn in general chemistry, right? The octet rule, or the 16 electron rule for larger systems. Determine bonding, and core electrons do not participate. All right, so that means that if we want to think about the bonding of molecular nitrogen, we probably don't have to worry about the 1s orbitals very much. We'll see that very quickly. One thing, however, the core electrons do affect one thing. Core electrons affect the energies of the valence electrons. Via something called shielding. Okay, what do I mean by shielding? Well, let's think about helium and then the next atom after that, lithium. All right, that's a really good example. All right, so let's think about how electrons build up from hydrogen, helium to lithium. All right, so for instance, hydrogen, of course, just has one s electron. It's 1s1. Helium is 1s2, right? So we have a half-filled valence shell for hydrogen. Right, the S is half-filled, and of course this is a full-filled valence shell. All right, and then what happens in sodium? Well, I take the helium atomic electron structure 1s2 and add 2s1 to it. Okay, so now I have a half-filled valence shell. Right? And so the question is how do these electrons in the 1s affect the 2s electrons? And the fact of the matter is that if you look at the atom like from a shell structure, you have a nucleus here, and on the interior of it you have, sometimes you do this in spherical shells, which is again not a reasonable, it's not a true model of the system, but it's a good way to think about it. You have two 1s electrons in this inner shell. Right? And then the 2s shell, it turns out, is quite a bit further away. Right? So the 2s's are out here. And so the 2s electrons, instead of seeing what they actually see when they're attracted to whatever's in the core, right? These 2s electrons here, this 2s electron is attracted to whatever's in the core. But what's the core? It's not just a nucleus. It's not just protons, but it's also two electrons as well. So what's the net charge of the new core here? Well, you have -2 from the electrons, and then the nucleus has 4 protons, right? 3 protons, not lithium, excuse me. Lithium has 3 protons, right? So the nucleus has a net charge of 3, and so the whole thing looks like a +1. Right? So the whole core, if you just blur it out, looks like a core that has charge of +1, and then on the outside you have an electron. Right? So lithium looks a lot like hydrogen. Right? It has a net charge. It has a net charge of +1 in the core and 1 electron in the outside. Right? Just like hydrogen. Right? +1 in the core, -1 in the valence. And so it's hydrogen-like. But the fact of the matter is that there is still an additional force here. So it's not just, you don't have just a nuclear valence electron attraction like you would in hydrogen, right? Hydrogen, in a hydrogen atom, all that you have is a proton and electron. That's all you have there. The charges are the same. But you also have small electron-electron repulsion. Right? So naively, you would think, okay, lithium looks a lot like hydrogen, just like a big hydrogen. But there's also a term here where this electron in the 2s orbital is interacting with the 1s orbital electrons as well. They have some effect. And what that leads to is I'm going to make sure I get the ordering right. I apologize. Right. Right. What it leads to is a increase in the 2s energy relative to hydrogen, and a decrease in the 1s energies. Right? So the spacing between the 1s and the 2s increases relative to hydrogen. So if I were to draw the 1s here and the 2s here for hydrogen, the energies for lithium look like this. So the 2s energy is slightly higher than you would expect for hydrogen, and than you would for the equivalent hydrogen case, and the 1s is deeper in the core energetically. Okay, and this is what's called shielding. Basically what happens is that the core electrons bind very tightly to the proton and act as a shield for the 2s electrons. So the 2s electrons can't penetrate into the core to get that positive charge from the protons, and so it effectively sees a weaker positive charge in the core, because those electrons on the outside shield it. The core electrons shield it, and that raises the energy of the 2s orbital, because those 2s electrons aren't as attracted to the core as you would expect. Likewise, it lowers this as well. So you get an equal and opposite effect here. The 2s goes up and the 1s goes down in lithium. Right? So the 1s electrons are dug deep in there, and the 2s electrons are more valence-like than you would expect from hydrogen. Right? This is called shielding. Right? And this happens in all atoms. All right, we'll look at that as we go through the second row. We start looking at different types of diatomics. We'll see that these orbitals change in energy as we go from atom to atom due to the shielding effect. Okay, so let's go back to nitrogen now. And what I can do is use spectroscopy to figure out how deep those electrons are in nitrogen. Right? I can map out by ionizing nitrogen how deep the electrons are. Because if I know how much energy it takes to remove an electron, I know where its orbital is in terms of energy. So for nitrogen, the 1s2 energy is around 100 eV, minus 100 EV. Right? It takes about 100 EV to kick that electron out. Remember that the ionization energy of hydrogen is 13.6. So I'll just do this comparison. So removing an electron, the bond strength of the electron in hydrogen is 13.6 eV. Right? And so the 1s and nitrogen is really, really deep down in there. Right? It's way, way deep down in there. It's embedded in the core of the atom. Right? And then the 2s2 is at minus 18 EV, and the 2p3 are at minus 12 EV. Of course, 0 EV is ionization. Right? That 0 is where the electron leaves. This is how deep they are relative to it. So, interestingly, here's another rule I'll add as well. Atomic orbitals tend to mix or interact with those that are nearby in energy. Okay, so for instance, when we add two nitrogens together, we have a nitrogen here that has electrons at these energies. The 2p orbital, for instance, is never going to interact and mix with the 1s orbital because they're at hugely different energies. You can calculate that integral. It's vanishingly tiny, but we don't even have to do that. We just say they're close to energy. They're so far apart in energy that the 1s2 electrons have no interactions with the 2p's. So when I draw a molecular orbital diagram for this, I won't connect the 1s's to the 2p's to form molecular orbitals because they're so far apart in energy they don't even talk to each other. Okay, this is an entirely different world than here. All right, so the 1s's, for instance, are only going to talk or mix with other nitrogen 1s orbitals. Right, so the 1s's are just by themselves. So let's do that. Let's take the 1s orbitals of nitrogen. And on my plot here, there's a minus 100. And we have two 1s orbitals. We know how these add together, right? These are two spheres. They add together like this. We get a bonding sigma orbital and an anti-bonding sigma orbital. We can look up online how much energy these are different by ionizing nitrogen as well, but let's not do that. And let's fill the shell, right? We put the atomic electrons into the molecular orbitals. 1, 2, 3, 4, right? This is why core electrons don't participate in bonding, because the core orbitals are alone. They don't interact with anything else but themselves, and they're completely filled. So when you fill the molecular orbitals with electrons, you put the same amount of electrons in the bonding as the anti-bonding. So these don't do anything, right? There's no net bonding here. Like the bond order is 0 in the core. Okay, so now what we have left are the 2s's and the 2p's. So I'm going to break the scale because I don't have enough room to do this right. Because when we were at 100, now we need to go up to minus 18. We have two 1s orbitals, two 2s orbitals here. And of course, they're both filled. And then at 12, we have three 2p's. And of course, by Hund's rule, the way these are filled is that they all have one unpaired electron. Like that. Okay. So now the question is how do these interact? How do the 2s's and the 2p's interact? So let's look at that. Let's use a little bit of geometry about how we know these orbitals look to see if we can figure out how they add together. So let's first add the 2s's and the 2s's. Well, we know exactly what that looks like. Right? You take two spheres. They've got a hole in the middle because there's a node, but that's okay. And you get a spherically symmetric, roughly a spherically symmetric orbital, an antibonding orbital. And we get a antibonding as well. So we know that the 2s's combine to form a bonding and antibonding pair. So I'll write 2s minus 2s here. And this is 2s plus 2s, sigma. Now how do we fill those up? Well, that's not too hard. They just go like this. Oh, let's not fill electrons yet. Sorry. Let's not do that yet. I'll come back to that. We haven't actually filled out all the orbitals yet, so remember we're going to have to fill them lowest energy to highest energy. So we'll come back to the orbitals in a second. Now we have to deal with the p's. All right, how do the p's add? All right, well, we haven't looked at p's yet, but p's aren't too hard. So we have three p's, three different p orbitals. Let's define. We have to set what our axis system is. Right, to define what z, x, and y are. So let's define our coordinate system like this. Right? X is out of the board. So we have, and again, our p. So we have 3 p orbitals. They're both half filled. They're all half filled. There's the py orbital. Now the py orbital has 2 phases. There's a positive one and a negative one. That's why I draw them 2 different ones. This is a negative phase and this is a positive phase. They're lobed. They're lobes of different. The wave function has lobes of different symmetry or positive or negative value centered at the origin like this. We have the px, which again is sticking out of the board. Again, it's the same orbital, it's just rotated 90 degrees out of the board. And the pz orbital is along the axis of the board. Okay. So now let's add them together. So let's try px plus py. All right, let's just try to pick random combinations. So py looks like this. And px looks like this. It's kind of hard to see, but if you put them on top, if you overlap them together, they're perpendicular to each other. All right, so all of the density in py is in the y-axis, and all the density in the x-axis is here, along this. And so they don't actually integrate to anything, because they're orthogonal. So what you get when you add them together is 0. They don't interact at all. They cancel out completely. All right, so we won't form a molecular orbital between px and py. All right, and not surprisingly, this is also the same for py, pz, and px plus pz. Right? They're all orthogonal to each other. It's not hard to think about, but if you have a lobe system like this and one like this, whichever way you do it, they're all 0. All right, so there are no interactions between these. All right, so those orbitals, those molecular orbitals don't exist. Same thing for the negative, well, the antibody combination. So we have 3 sets of orbitals that don't interact with each other, but of course they interact with themselves. So if we add 2 pz's together, like that, well, they add together very nicely. Right? The net result is something that looks like an s orbital with 2 really small lobes on the outside like that. Okay, so this is cylindrically symmetric as well. So this is a sigma orbital. So pz plus pz gives you a sigma orbital. And not surprisingly, when you do the subtraction, which looks like this, like that, now you're adding a positive to a negative. That cancels out in the middle, and you boost the amount of probability on the outsides. Something like that. And this is, of course, antibonding, sigma antibonding. Right? They cancel each other out in the center. They cancel out. They're different signs. Okay, so the pz orbitals, when you combine them, form 2 sigma orbitals. So we can go ahead and do that. Let's write these pz. Let's make sure I have my ordering right. Yep. So the pz's interact very nicely. We have the sigma here and the sigma star here. Okay. Now we have the px's and the py's. Again, they're the same thing, they're just rotated on 90 degrees, so we can look at either one and it's fine. Same as, let's just write that as congruent. And so that's like this. So if we add two py's together, it looks like that. And we get a system that looks like it has a big lobe on the top above the bond and a big lobe on the bottom of the bond, and you have a nodal plane basically where it's zero in the middle like this. Okay, because when you add together, there's no density in the middle of the bond, it's on the outsides. All right? So this has, again, some cylindrical symmetry, but it's got a node through the middle like this as well. So it's no longer spherically symmetric, and if I rotate by 180 degrees, I change the sign. All right, so it's actually odd or anti-symmetric. And we call these additions, things like this, called pi orbitals. So sigma and pi. Sigma are the orbitals, the molecular orbitals that look like s orbitals. And pi are the molecular orbitals that look like p orbitals added together. Okay. They have this kind of symmetry, centrosymmetric symmetry, where you have some density on the top of the bond or perpendicular above the bond and below the bond, but not in the middle. Okay. Whereas in the s orbitals, you have, in the s orbitals, where do I have it here? Right here, there's plenty of probability for the atoms, the electrons, to be in the middle of the bond, along the bond axis, right? But here there's a plane there where it's zero. So that's the difference between a pi and a sigma orbital, right? And so p orbitals form both sigma and pi, right? The ones that are face to face like this, the z orbitals, they form a sigma combination, and the rest of them form pi combinations. And so two of them support that, right? You add the px's together, the py's, and you form equivalent pi orbitals. So we form two pi orbitals here and two pi star orbitals, like so. We've missed one thing, a very, very small effect. There's one combination we haven't added, and it's a small change, but it's an important one, is that you can add 2s to 2p. How would we do that? So here's my 2s orbital. And now I want to add it to one of the p orbitals. All right, so let's pick. So we could do it this one, py. We could do it with the px, which is the same idea, but just rotated. Or we can do it with the pz orbital. Okay, so one thing that you can think about is that you're taking a sphere and overlapping it with this lobe-like structure. And so when you overlap them, again, this is all positive, and this changes signs at the atom. Right? You have a sign change here from positive to negative. So when you put the sphere on top of this symmetric object that changes signs, the top half is going to be some overlap, and the bottom is going to be negative that. Right? So this top half, let's say you get a positive integral, and then on the negative half of the integral, you get a negative, equal and opposite negative. So the net overlap is 0. Right? The positive part added to the sphere cancels out the negative part added to the sphere. Same for px. Right? So the s orbital doesn't mix with the x and y because of the cancellation. But if you notice here with pz, we don't have that luxury. Because now you have a lobe of a specific sign pointing towards the s orbital. Like that, these have constructive overlap and destructive overlap, right? You get this one, which is a bonding, and you get one that's anti-bonding, which is where the signs of the wave functions have changed, like this. Right? These can add together, right? So you end up getting something that kind of looks like this. This is a sigma orbital. This is pz plus s. And then you get an antibonding one where these cancel each other out, which kind of looks like, well, that's not a very good drawing. that, and then this lobe gets smaller like that, and then you get a bigger lobe on the outside like this. Sigma star. PZ minus S, or S minus PZ. Right? So you get a bonding and antibonding pair of those as well. But this does not mix nearly as well. So what we actually need to draw here is, in fact, this also contributes to this orbital as well. And to this, the sigma orbital between the P's as well. There's also a connection here and also one here. What that does, though, is it causes, actually what happens is, it causes is that the S's and the P's start to blur together. The S and the P, in fact, they're not separate. The PZ and the S orbitals aren't really separate anymore. They're actually kind of, what you should represent it as is a mix of the two. And all that does is it changes the energy ordering of these orbitals. So what I'm doing now is I'm mixing S and P together and PZ together. So really the way I should draw this, these atomic orbitals, is you have 2px, 2py, they interact by themselves, and then you have a positive 2pz plus 2s combination and a negative 2pz minus 2s combination, right? So what happens is that the pz orbital and the s orbital mix, and now you have a new set of atomic basis functions that are actually a combination of the two. And that changes the energy of the atomic orbitals. So you have two high energy px, py orbitals that don't move, and then the pz orbital energy decreases and the s orbital energy increases like this. And so what you would instead have is something that looks like this. 2pz plus or minus s. And so what happens is that when you move all of the, what happens is when you mix these, the energies of the molecular orbitals change. You still have the same molecular orbitals, but now the energies that they come out are slightly different because now your wave functions that you're building from are slightly different, so the integrals change. And what you're left with is, in fact, that the sigma orbital that was up here actually lowers in energy like this. So again, you still have this strong sigma-sigma star bonding from the 2s combination in purple. And then now you have these sigma orbitals that are coming from the pz mixing with the s, and that closes their energy in a little bit like this. So this is what the molecular orbital structure looks like. So I can get rid of this, for instance. And now we can fill with electrons. Okay, so how many electrons do we have left? 1, 2, 3, 4, 5. And then we have 1, 2, 3, 4, 5. So we have 10 electrons to fill in the valence shell. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now let's calculate the bond order of this system. All right, so what's the bond order? So the bond order is 1/2 the number of bonding electrons minus antibonding electrons. Okay, so again, all of these cancel out. We have, in the 1s, these don't even matter, right? We have 2 bonding electrons, 2 antibonding, they cancel out, so we can just ignore that. Now, how many bonding electrons do we have here? Well, we have 4 bonding orbitals. We have 1, 2, 3, and 4. So we have 8. And then there are 2 in the antibonding sigma orbital, right? So that's 1/2 times 8 minus 2, and that's 3. We have a triple bond. Right? So that's exactly what we would expect, right? Nitrogen has a triple bond. Like so. These right here, actually, these pi electrons, Do I want to say that? I don't want to say that. Right? Okay. Right. So the triple bond arises from, you have a single bond, right? Here's your single sigma bond, and then you have two pi orbitals, the x's and the y's, that form the double bonds. Right? So nitrogen has the sigma bonding in the plane, which is 2pz plus s, 2s, the mixes. And then you have these p orbitals that stick out like this. Let's call that px, px. And then you have ones that stick out of the plane like this that overlap each other as well. That's the py. Doesn't matter what order you do. Right, so we have a single bond through the bond, the sigmas. We have a double bond through this perpendicular set of pi orbitals. And then we have the triple bond out of the board. Right, so we have a pi orbital in the plane of the board, one on the outside of the plane of the board, and a single bond going through the middle of the molecule. Right, there's our triple bond. Okay, let's prove that this is the case. Oh, I don't have my computer up. Oh, okay, never mind. Anyway, you have to trust me that this is correct. It is. Interestingly, this was not a trivial problem in recently as the 1960s. I actually, during my PhD dissertation I found a story about molecular nitrogen. Someone wanted to calculate this molecular orbital diagram using what's called a minimal basis, right? He added the 1s, the 2s's, and the 2p's together, and to solve the Schrodinger equation for this molecule and get all the orbital energies. Right? Wants to calculate this molecular orbital diagram for nitrogen. In the 1960s, all they had were computers with vacuum tubes. Right? All of your programming was done on little punch cards, and back then you could barely even just to do a matrix calculation took months. It was very, very slow. I mean, we're talking, right, your phone is hundreds and orders of magnitude more powerful than these computers were in the 1960s. And so they went ahead, so it was his PhD work or his postdoctoral work, I can't remember the guy's name. He was at the University of Chicago working for Robert Mulliken. And decided, I'm going to go do the calculation. I'm going to calculate the energy of nitrogen in the molecular orbital structure of nitrogen, right, using a minimal basis, the exact same basis of electrons and orbitals we use here. And it was him and 3 graduate students to do this calculation. It took them 3 years. Right? It took them 3 years to calculate this from first principles. 3-year project just to calculate nitrogen. I could do this calculation in better accuracy in less than 5 seconds on a computer now. Right? So it's really amazing how far we've gone. But again, we don't have to do complicated calculations. We can just use basic geometry of atomic orbitals to add them together to have sense of how they add and subtract to each other. Right? How do they cancel each other out? What orbitals interact with which orbitals? Right? We can have these simple rules and we can come up with these qualitative diagrams. If I didn't know that the S's and the P's mixed, then I might get the ordering wrong here, but that's not a big deal, right? I still encapsulate the important features of the molecule, right? That it has a triple bond, and that whether this sigma star orbital is below or above the pi orbital will ultimately determine the structure of the molecule, but the pi orbital is actually higher in energy. So again, we need to use a little bit of empirical knowledge to be able to determine these subtle differences. But again, I only have to use these very qualitative ideas to be able to start to construct this. Okay. Any questions about that? How are we doing on time? Good. So what I want to do now is I want to move to oxygen. All right? And again, oxygen is not so much different. The only difference between oxygen and nitrogen is you have an extra electron. Right? Oxygen is 1s2, 2s2, 2p4. So what I can do though, the interesting thing though is that I can't just use this molecular orbital diagram because now I've added 2 electrons to the system. Right, there's more valence electrons in the shell. They interact more with the core electrons, and that's going to change the energies of these orbitals. Right? The orbitals of oxygen, the atomic orbitals of oxygen aren't necessarily the same as nitrogen, and that's going to affect the results. But here's something that's really interesting about oxygen. So if I were to, let's look at this region here, kind of this region right here, this kind of valence region of the shells, right? And so for nitrogen, nitrogen has these are the pi bonding orbitals, and then there is a sigma star antibonding orbital, and then 2 pi star, empty pi star nitrogen. So this is nitrogen. All right, so all I've done here is taken these orbitals, this orbital, and these 5 orbitals right here in the valence shell. Right here, and I've moved them over there. Okay, so this is what nitrogen does. As you go up the periodic table, or go down a row towards the noble gases, S plus P mixing increases, lowering the sigma star energy of this valence sigma star. It turns out that oxygen is the critical point. Again, you have 2 pi star orbitals at the highest energy, where the ordering of these two flip. So in oxygen, you have the pi orbitals next, and then the sigma star here below. Basically what's happening is that there is more S character in this sigma orbital, and so that pushes everything down towards the 2 S orbitals. The P becomes less important. Because the P's have more electrons in them, there's more repulsion, so the P orbital energy increases. The idea actually is that the P this energy increases due to P orbital electron repulsion. And this decreases in energy with more 2s character. All right, so what's actually happening is that the 2s orbital is actually decreasing in energy because it's more shielded by the stuff in the core, because you have more electrons. And so it just increases, this increases slightly, and then this decreases, and you get a flipping of the order. So let's fill in the rest of the electrons. O2 has 2 extra electrons over N2. Okay, so we can just fill up 1, 2, 3, 4, 5, 6, and we have 2 electrons left. There's only one way to fill it. Hund's rule says that they're half filled in the pi star. Right, so the interesting thing about oxygen is, again, now we're starting to put an extra set of electrons in an antibonding orbital. Right, we have an extra 2 electrons in our antibonding orbital, so we have 4 here. So now we have a double bond for oxygen, right, as you expect, right, because we have 2 extra pi electrons. But because of Hund's rule, remember the spin multiplicity has to be as high as possible. So the net spin of O2 is plus 1/2 plus 1/2, which is 1. What is the net spin for N2? Well, it's 0, right? They're all canceled out. Right? Plus 1/2 minus 1/2, 0. So net spin here is equal to 0. And then, so that means then that the multiplicity, 2s plus 1, is 1, which means that nitrogen is a singlet. And for O2, 2s plus 1 is 3. We call that a triplet. So oxygen, because of these extra electrons and the position of the pi star orbital, we predict O2 to be a triplet, which means that oxygen is magnetic. Right? Something I recommend doing if you've never seen it before is to go online. There's tons of people who've done this experiment. If you take a magnet, a permanent magnet, and then pour liquid nitrogen over it. You put a magnet on a table and then pour liquid. Actually, maybe it's better to have a table or a bowl or something like that and pour liquid oxygen into it. And then put a magnet on top of that liquid and it floats because oxygen is magnetic. And so it'll actually repel a magnet. A magnet will sit there and float on top of the liquid oxygen because it's a magnetic material. Right? And the only thing that makes it magnetic is the fact that we've got 2 extra electrons and they go into this pi orbital and they have to go in such a way that they add spin up, or then they get spin paired, or unpaired spins. Right? So this, by necessity, just from the molecular orbitals, oxygen has to be magnetic. Right? So typically we write oxygen as 3O2, which means triplet. Right? There's also an equivalent isomer. We can also write, there's nothing stopping us from measuring to having that. Here, the net spin is 0, which is a singlet. Right? So there, in fact, also exists, we predict, there exists a singlet oxygen, we call 1O2, a singlet oxygen as well. Right? So all the oxygen you breathe is triplet. It's always magnetic. But if the energy difference between this and this, I forget exactly what it is, 50 or 60 kilojoules per mole or something like that. But there's an energy difference between these. The reason why there's an energy difference between these is that these 2 electrons can't interact with each other because that would mean that they exist in the same place. They can't do that. Right? You can't have the same electron in the same state in the same space, right? So they're away from each other. They don't interact with each other. And here now you have paired electrons of different spins. They can be in the same spot as each other, and they're going to push each other apart. Right? So you have repulsion here because there are different spins, and here there's no electron repulsion between these 2. All right, so this is a lower energy system because those 2 electrons can't talk to each other, but these can. They can repel each other. They can be in each other's space. And so they repel each other, so it's slightly higher energy. All right, so singlet oxygen does exist. In order to go from triplet to singlet oxygen, you have to heat oxygen up to like 1500 Kelvin. All right, it has to be very, very high temperature. But you can convert between singlet and triplet. Interestingly, singlet oxygen is super, super reactive. Right? Singlet oxygen will oxidize just about anything. And the reason why is because oxygen wants to be a triplet, and so it'll do just about anything to break this apart. Like that repulsion between those 2 electrons really start to break that bond, really weaken oxygen. And singlet oxygen is like an ultra oxidizer, super powerful. It'll add atomic oxygen to just about anything you throw at it. So regular oxygen, the oxygen we know and love, is not particularly reactive because again there's no repulsion in the upper orbitals, in the valence shell. Those electrons can just coexist peacefully, but they want to press each other apart in singlet oxygen, so this system wants to break apart very quickly. It's very, very reactive. Very reactive. It'll break apart into two oxygen atoms and add oxygen to pretty much any hydrocarbon you throw at it. All right, this is one of the big sources for strongly oxidized material in combustion. If you add triplet oxygen to a clean burning fuel, typically what happens is you form CO2 and H2O, right? That's the ideal. But if you react it with singlet oxygen, all the system wants to do is oxidize. So if you have a hydrocarbon, it just wants to make aldehydes and ketones and alcohols and stuff like that. You oxidize the crap out of it. It just injects oxygen into your system, and so you don't get complete combustion with singlet oxygen. Right, so you often want to avoid that for emission. You don't want your exhaust temperature, your catalytic converter temperature so hot in the combustion process that you generate spontaneously singlet oxygen, because that won't help combustion. It will just oxidize out all your hydrocarbons. So you always want to keep your catalytic converter temperature down low enough so that you can complete combustion without having singlet oxygen in your system. All right, again, none of this is quantitative, right? All I've done is just I've used some simple rules, added orbitals together, and I can come up with all sorts of chemistry things, right? All sorts of interesting comments about chemistry by just looking at these molecular orbital diagrams. We'll look at this more carefully. Right? We'll come back to this idea over and over again, molecular orbital diagrams, and we'll be able to learn a lot about chemistry. When we get to organic molecules, we'll look at hydrocarbons, conjugated hydrocarbons, things like benzene, double bonded systems and stuff. We can learn a lot about how they react just by looking at their orbitals. Right, we'll look at, hopefully I'll have some time to do, if you guys remember from Orgo 2, Diels-Alder chemistry, 4+2 cycloadditions. I don't know if you remember this, but when you add a system of 4 pi electrons and 2 pi electrons, it's thermodynamically favorable. That's called the Diels-Alder reaction. But you can't mix two 2 pi electron system with a 2 pi electron system, a 2+2. That's not allowed. And the way that you determine why it's not allowed or not is through a very simple argument with molecular orbitals. Right? And in fact, there was a Nobel Prize for that exact argument. Bob Woodward and Roald Hoffman, where they came up with a very, very systematic set of rules about how can you add hydrocarbons together using cycloaddition rules, things like Diels-Alder. When do you need light, or when can it be done thermally? Right? And they use a molecular orbital argument for the whole thing. Right? They just use molecular orbitals to argue reactivity. So I'll try to summarize this. It's a really beautiful study. I'll try to talk about it in the next couple weeks. Okay, how much time do we have left? 15 minutes? Great. So I want to look at one more quick example for diatomics. And then starting Monday, we'll start with hydrocarbons. All right, we'll look at methane, and then we'll start putting methanes together to make more interesting molecules. And then we'll do organic chemistry from the ground up. So again, all I've looked at so far are homonuclear diatomics, right? Where both atoms are the same. All right, so that's nice, but of course, that only constitutes a very, very small fraction of molecules, even diatomics. So it might be worthwhile looking at something where both atoms are different, heteronuclear diatomic. All right, so the one molecule I want to look at today is NH, the NH radical. All right, we're going to add an N and an H together. We're going to take our nitrogen knowledge and our hydrogen knowledge and put it together. Okay, so again, we need to apply our rules. Right? We're going to look at the valence shell only, and we need to combine orbitals that are close in energy together. Okay, so let's draw a little diagram here. Let's put hydrogen on the left and nitrogen on the right. Okay, and let's think about where our orbitals are for nitrogen, or hydrogen, right? So the first one, of course, is the 1s orbital. That's at minus 13.6. All right, so we have a hydrogen orbital, 1s orbital here, with 1 electron in it. Let's go ahead and put the 2s orbitals, 2p, they're at minus 3.4. There's 1, 2, 3, 4 orbitals there, no electrons in them. And then what about nitrogen? Well, we have the nitrogen numbers over here. Nitrogen has a 2s orbital at 18 and a 2p orbital at minus 12. So the 2s orbital, I'm going to have to lower it just a little bit, is down here. This is for nitrogen. Right. But we do have some 2p orbitals at minus 12. Look right here. So we have nitrogen 2p at minus 12 eV. Okay, so, and again, let's fill these. Nitrogen's 2s orbital is completely filled, and we have 3 electrons here. All right, so how do these add? Well, the 2s orbitals are too far up, right? These are so far away that they're not going to interact much with this. This is so deep that it's probably not going to interact with this. So the only thing that's going to happen in this molecule is the 1s is going to interact with the 2p's. All right, so how does that work? Well, the only combination that works is the 1s plus 2pz, like that. The other ones cancel out. Right, so let's do the cancel ones out. Those 2 orbitals, the px and the py, just sit right here. They're non-bonding orbitals, right? They don't interact with anything. They're just sitting there by themselves, right? The px and py. But the pz interacts with the 1s. All right, but there's a bit of an energy difference between the two. And if you think about it, the nitrogen, we should basically create an interaction here that is equal increase as it is decrease. And so what's going to happen is that the stabilization energy from here is going to equal the destabilization energy from here. So this is going to lower by some amount, and this is going to increase by some amount. So when I draw this, let's say it decreases by about an eV or something like that. I'm going to form an s orbital here, a sigma orbital here, a bonding sigma orbital. And then an equal distance up from the p orbital. Let me draw them a little bit in the center. Sigma orbital here, and a sigma star orbital here. Like that, right? So these are our combinations. Right? I've decreased this energy, I've decreased the bonding energy by this much, and therefore I have to increase the antibonding energy by this much. But notice what's happened in terms of energies. This orbital looks more hydrogen-like, right? It's closer in energy to the hydrogen orbital, and that means that it's more of a hydrogen-like bond, or hydrogen-like orbital. So what that means is that most of the distribution of where the electrons can be is on the hydrogen side. Meanwhile, on the antibonding orbital, this is more nitrogen-like. All right, so let's fill up. We have, how many electrons do we have? We have 1, 2, 3, 4. So we fill up 1, 2, 3, 4, like that. All right, so what do we know from this molecule? Well, it has a bond order of approximately 2. So it's NH. Right? But it has 2 unpaired electrons in non-bonding orbitals, like so. Well, actually, it's more like this. There's a there's a sigma bond, there's a half double bond, so it's actually this, like this. There's a lone pair. Or no, there's not. And then there's two like this as well. Right? So there's kind of like there's actually an unpaired electron in this p orbital, localized on the n. This is the py, if you will, and then there's one out of the plane, the px, like that. Right? So it's a diradical. And it has a single sigma bond. All right, so we expect this to be a triplet. Right, spin is 1. All right, so it's a radical. But interestingly, what's happened is that now this bonding orbital is very hydrogen-like. It doesn't really look like a nitrogen bond. It doesn't look like a nitrogen, right? Because it's close in energy to the 1s orbital. That means that it looks like the 1s orbital, right? So the orbitals for this would look more like this. So let's think about where we start from. Oh, I need to connect this here, like that. There we go. So here's my 1s orbital. It's a sphere. And then my 2pz looks like this. This is my nitrogen 2pz, and this is my hydrogen 1s. We add them together. And the resultant looks a lot like hydrogen and not like nitrogen. So in fact, what this looks like, here's my hydrogen, here's my nitrogen. It's kind of bulbous. There's a little small node here, something like that. Right, it's polarized towards the hydrogen. The electrons tend to exist. Hydrogens localized near tend to be hydrogen-like. Right? So they don't really subsist around the nitrogen. And maybe that's a reasonable thing to think about, because the other electrons in the valence shell that are being that are there are these two unpaired ones in the p orbitals on the nitrogen. Right? This nitrogen has two p orbitals like that each have an unpaired electron in them. Right? If you think about the electrons in this 1s shell, they're going to want to stay far away from those. Right? There's a lot of repulsion between these electrons and these. Right? So because these lone pair electrons, they're not interacting and bonding at all, they're just sitting on the nitrogen by themselves, that wants to polarize all the other electrons away as far as possible from them. So it's hydrogen-like. Okay? And likewise, the antibonding orbital, all of them are going to push towards the nitrogen. Right? So the antibonding orbital for this combination looks a bit like, let's see if I can draw it. So here's my hydrogen, here's my nitrogen. Let me get a different color. There's a very small lobe on the hydrogen, right? Because this is nitrogen-like. It's going to be, let me think about this for a second. Something like this. So bonding cancellation there. And most of this is your nitrogen and this is your hydrogen. So very little about this amount of stuff on the hydrogen and a lot on the nitrogen. And so you kind of have a lot of amplitude that sits on the nitrogen. Like that. So it's polarized the opposite way. And maybe that makes sense. Because if I took one of these electrons and put it here, I'm promoting an antibonding-like arrangement. I want to break that bond. And what's going to help push me towards breaking a bond while being nearby two electrons that are unpaired and localized at the nitrogen, these radical electrons, the free radical electrons. Right? So this nitrogen-like antibonding orbital is very close to the nitrogen lone pair, or the unpaired electrons in nitrogen from the radical. And so that nitrogen so the antibonding effects, if you will, the things that want to break the bond are very localized towards the nitrogen, because that's where all the repulsion is. Right, so this is repelled. These are both repelled by, so this is, I would say that the antibonding is promoted by atomic nitrogen electrons. And here, bonding mitigates interaction with those electrons. Another way to look at this, and this is kind of a chemical way to approach it. Another way to look at it is in terms of electronegativity. You have a lot of negative charge here and a lot of positive charge here. You have a large amount of electronegativity going in this way. And so that means when you combine, all that's saying is that when you combine the electrons, or combine the atomic orbitals, that the resulting molecular orbitals are going to be polarized towards one direction or another. And so the bonding electrons are naturally, you want to go towards the hydrogen because that's where there's the least amount of electron density, right? The hydrogen is electron depleted compared to the nitrogen. So there's more space for negative particles, negative electrons in the hydrogen region, right? So that polarizes those electrons in the bonding orbital towards hydrogen because that's where the charge, there's least amount of charge there, right? They don't want to be near the nitrogen because the nitrogen is electronegative. Right? Likewise, when you excite things and you want to break it apart, that means you want to jam as much negative charge into a negative region to break that bond and to weaken it, and that's why the antibonding orbital sits near the nitrogen. It's nitrogen-like. Right? So there's different ways to interpret this. What someone would, the real way to say it is the reason why nitrogen is so electronegative compared to hydrogen the reason why this occurs is a product of the fact that the molecular orbitals are polarized like this, right? So I'm going, this is a consequence of this, but the way I've been talking about it here is that this is a consequence of this, right? But they're the same effect, effectively, right? This idea of electronegativity isn't really a meaningful concept. It's an empirical number that allows you to track how bonding and antibonding orbitals polarize with respect to one or the other atoms, depending on their electron density at the beginning, right? Nitrogen is electron rich, hydrogen is electron poor. And so if you're gonna pump a bunch of electrons into a region where it's going to be bonding, you better hope it's in a region that's very electron poor, because that's where the electrons want to go. Right? Electrons want to fill that region. So it's kind of like that the nitrogen donates. This is an organic chemistry way. Nitrogen donates electrons to the hydrogen. Right? And that means that the hydrogen bonding electrons are more hydrogen-like, because that electron density is being pushed towards the positive region of the molecule, and vice versa for the antibonding. Right? All of these arguments are equivalent. Right? I've given you an if and then statement for these, but in fact you can do it the other way around. It just depends on how your perspective. But a quantum chemist would argue the reason why nitrogen is so electronegative is that when you bond it with something like hydrogen, its bonding orbitals tend to be very polarized towards the more electron poor element. And so this polarization, this hydrogen-like bonding orbital, is actually leads to this result of electronegativity. So it just depends on how you look at it. Electronegativity was developed before anyone understood this picture, as this picture was much later. Right? So this is an empirical idea that people came up with, but you can justify it by the fact that the molecular orbital diagram is designed this way. This is the way that this is the absolute truth, if you will, and this is a way to empiricize that. This is an empirical observation of this effect. Okay, so again, the idea is that polarization in bonds, dipoles, what makes a polar functional group, what makes a nonpolar functional group, what makes an electron withdrawing group, what makes an electron donating group, all comes down to relative energies of atomic orbitals that you add together. And typically in electronegative atoms tend to have a lot of electrons in very high energy valence shells, and they're interacting with atoms that have much lower valence energies like hydrogen, and then you end up getting these polarized bonds where one looks a lot like one atom and one looks like another, and not like a mix of the two. And that's what causes polar bonds, right? The CN group, for instance, the nitrile group is a great example of something that polarizes your molecular orbitals one way or the other, or other types of things, OH and Cl and fluorine and things like that, right? Fluorine has very, very high 2p electrons, 2p orbitals, and so when they interact with a 1s orbital on a hydrogen, they polarize the bonding way, way towards the hydrogen, and therefore it looks electronegative. It looks polar, right? But I'm just saying the same thing in two different ways. Okay, that's all I have for you today. So what we'll do on Monday is we'll return to this idea, and instead of doing diatomics, we'll look at methane. We'll put methane together, and then we'll put 2 methanes together, and then we'll put 3 methanes together, and then we'll come up with a way to analyze a system for arbitrary numbers of hydrocarbons. A really, really simple approximation that'll give us some really, really nice qualitative results. All right, homework's due on Friday. There will be another problem set next week, which will be our last problem set of the year. Have a lovely weekend. You too, thank you.